All right, welcome back to the video on enzymes. In this video, we're going to be talking about enzyme activators and inhibitors. One of the things I notice as I go back and I'm making all these videos over the summer, and I go back and I listen to them, is that I use the word a lot, and it's probably annoying. And I apologize that you've had to listen to several videos now with me saying every few seconds. But it takes a lot of time to create these videos, so I don't really want to go back and remake them. I am going to try to consciously curb my ums. Thank you for being patient and listening thus far with all the videos, as annoying as they may be. Cooperativity. Oh, there we go. Cooperativity. I have a really hard time saying cooperativity. A substrate, remember the substrate is going to turn into the products. An enzyme is a catalyst, so it is going to speed up the rate of a reaction. The substrate is going to bind to one part of the enzyme, which is going to trigger a shape change in the subunits of the enzyme. Note that the subunits of the enzyme, an enzyme can have more than one active site. Okay, it can be comprised of several. That's going to amplify the response of the enzyme to the substrate. So that's actually going to help the reaction speed along. Allosteric regulation means, proteins function at one site affects the binding of a regulatory molecule at a separate site. Remember, we can have regulatory molecules, and we talked about in the last video, cofactors and coenzymes. The protein function at one site affects the binding of a regulatory molecule at a separate site. This can actually activate the enzyme, or it can also inhibit the enzyme's activity. So here is an example. So let's talk first about the cooperativity. In this example, the substrate here is going to bind to one active site, and that's going to stabilize the rest of the active sites so that they can allow the substrate to bind there, and it can activate the enzyme, or it can speed that up. It can help the enzyme. In this case, we've got allosteric either activation or inhibition. So let's do the activation first, because that's what cooperativity is. Here you have an actual separate activator. It's not necessarily the substrate. It's actually something else. This activator is going to bind, and that's going to cause all of these active sites to remain active. They're going to stabilize it. Okay? Now, something else can happen if you have an inhibitor. An inhibitor can bind to the enzyme, and that can actually cause an inactive form of the active site. The active site can remain inactive, and that will keep it or stabilize it in that inactive form. If it's an inactive, substrate is not going to bind. Okay, that's why we call it inhibition, because it's inhibiting that from happening. Now, there's two types of inhibition. Certain chemicals can inhibit the action of a specific enzyme. There are competitive inhibitors. These actually block the substrates from entering the active site. And then there are non-competitive inhibitors, which impede the enzymatic activity by binding to another part of the enzyme, which causes the enzyme molecule to change shape so that the active site becomes less effective. So it's not competing for the same active site, but it's going to change the shape of that active site so that it can't do what it's supposed to do. So here are some examples of enzyme inhibitors. There are lots of toxins and poisons that are actually enzyme inhibitors. Nerve gas affects the neurons and transmission of neurotransmitters. DDT, that was, I think, a pesticide that was used long ago. Antibiotics, well, they're actually not hurting you when you take them. They are actually inhibitors of enzymes in bacteria. That's one way that they kill the bacteria, is they inhibit the enzymes. Well, if enzymes make chemical reactions happen in the bacteria, then if we inhibit the enzyme's activity, it's not going to allow that bacteria to survive. Naturally occurring in cells to regulate enzyme activity. For example, we've talked about before about lactose intolerant people. And we've talked about the enzyme lactase. Well, if you drink a big glass of milk, you're going to need some lactase. Okay? So you're actually going to affect or regulate that enzyme's activity. It's going to be more active when you drink a glass of milk than when you eat a carrot. Okay? So sometimes it's just naturally your body is going to regulate when enzymes are active and when they are inhibited. This shows the difference between competitive and non-competitive inhibition. Competitive inhibition, here's the substrate, and here's the competitive inhibitor. So the competitive inhibitor is actually going to take that active site over. It's going to compete with the substrate for that active site. Non-competitive inhibition is going to be different. The inhibitor is actually going to bind at a different location, and that's going to change the shape here. Okay, that's delta means change. It's going to change the shape here, and you can't hardly read the word shape. So that the substrate can't bind. Okay, that's the idea. Competitive versus non-competitive. Feedback inhibition. A metabolic pathway that is switched off by the inhibitory binding of its end product to the enzyme that acts early in the pathway. Okay, so what does that mean? I like visuals. So here's our initial substrate, threonine. It enters the active site of this enzyme. Remember that most enzymes do not go simply from substrate to product. They usually have intermediate reactions catalyzed by multiple enzymes. So we started with threonine, we end up with isoleucine, one amino acid to another. The isoleucine then is going to be taken in or taken up by the enzyme. It's actually going to enter the active site, and it's actually going to act as a non-competitive inhibitor. I'm sorry if you can hear my dog barking. There's people outside, and she's very upset about that. So it's going to act as a non-competitive inhibitor because it's not going to enter the active site or compete for the active site. It's going to bind somewhere else, and it's going to change that shape of the active site. And when it does that, it's going to inhibit threonine from entering that active site. So if we can't get threonine into that active site, then none of this is going to happen. We're not going to produce any more isoleucine. Well, you may be asking yourself, why on earth would you? That's probably a really good question. Why would you want to stop it? Well, maybe you don't need to make any more isoleucine because your body has enough. Maybe it will eventually stop that. And once there's not enough of this isoleucine again, then maybe it will revert back to allowing the threonine to enter the active site. There's usually a reason for why this works. Now, I'm not going to go too far into feedback inhibition because we do a unit on feedback loops. So we talk about negative feedback loops and positive feedback loops. And so we do go more into depth in this when we get to that unit later in the year. Oh, come on. I'm pretty sure it's the last one, but for some reason it's not switching here.